Okay, here we go. Let's start with talking about the stuff that I already expect you to know, which at this point you kind of have been like, all right, we know this. So at this point you should know all about ionic compounds, right? You should know the properties of ionic compounds. Why is this not getting bigger? There we go. You should know the properties of ionic compounds. Woo! Ionic compounds. You do. It makes it much more fun if you say, woo! Ionic compounds. I wonder if my dogs would come if I said that. Woo! Alright, so we know that they're called salts. We know that their electronegativity difference is greater than 1.7. Nothing new here. Nothing new. We know that they are made from a metal and a nonmetal. We know that they are high melting points and high boiling points. We know that they are usually crystalline solids. We know that they never conduct as a solid. But they do conduct as liquid or aqueous. You were close. Aqueous means mixed with water, because the conductivity of these things are based on the fact that the ions can move. And when they're solids, the ions are locked in place. Like if you have something that looks like this, the ions are locked in place. But as soon as the water hits it, and we're going to learn how to draw water today. Water kind of looks like that. Okay? The water molecules pull these molecules. One's going to go over there, and one's going to go over there. And now the water is separated the ions from each other, and they can move like that. I took the H with me. And because the ions can move, now we can conduct electricity. That's a popular test question right there. Why can these things conduct electricity? There's a special word for things that conduct electricity, and salts are this thing. Think Gatorade. Electrolytes. Electrolytes are substances that can conduct electricity. Water is not an electrolyte. Electricity. Water can't conduct electricity. It's the salts that are dissolved in the water that are allowing those ions from the salts to move around. That's what's conducting electricity. I also want to add here that when we're talking about ionic compounds, there is a transfer of electrons. They're going to go from the metal to the nonmetal. I'm abbreviating nonmetal. And you also at this point should know how to, let's move this up, let's resize this. You should know how to draw a Lewis dot diagram spell it right of an ionic substance. So let's say you have sodium chloride. Sodium has 1 valence electron. Chlorine had 7 valence electrons. You're going to show the movement of electron from one to the other. And then you're going to put the sodium in brackets with the positive charge and the chlorine in brackets with the negative charge. That's an ionic compound right there. That's how you draw it. Now, the reason I'm making a big deal about this, because we're going to start covalent compounds in about 15 seconds, And once I start those covalent compounds, the very first question you should ask yourself for every single question that you do is this ionic or is this covalent? Because if it's ionic, we've got all this going on. If it's covalent, we got something totally different going on. Okay? So, does everybody understand ionic before I get to covalent?
Yes.
Okay. Here we go. Covalent. What color you want? Covalent sounds like it's green. Okay. Co means like cooperation, sharing, okay? With, together. Valent is the valence electrons. So we are going to be sharing electrons. Whereas the ionic was transferring the electrons from the metal to the nonmetal, covalent is going to be sharing electrons between two nonmetals. Sounds good to me. We're going to start with a covalent bond between two of the same atoms, and we're going to start with hydrogen because it's the simplest one. But I'm going to write down the properties of covalent first, then I'll get into that. Okay. So now we've got covalent, where you know that the melting point and the boiling points are low. Think chocolate. Think soft and smushy. They are not hard crystals. Smushy, very technical word. Okay? Like if you put your finger into a Mounds bar, you even eat Mounds bars anymore? Where's the Mounds bar? That's the one with the coconut. If you put it into a, give me something. A marshmallow. It's smushy like that. I like it. Marshmallow. Okay? So that's covalent. Their electronegativity difference is going to be less than 1.7. I didn't write soft and smushy. And these suckers never conduct electricity. Doesn't matter where they are. They never conduct electricity. A marshmallow, you can stick it in an electric socket, it's not going to conduct electricity. I don't know how you would ever do that, but give a marshmallow to a toddler, they'd probably figure out a way. You know it, right? Who babysits little kids? They do some crazy things, don't they? You're like, what made you think that would be a good idea? They just look at you. Anyway, so covalent, they never, ever, ever conduct electricity. So we have, listen carefully, covalent never conducts electricity. Ionic conducts it only when it's in liquid or aqueous solution. When do metals conduct electricity? Always. So metals are always, covalent is never, ionic is sometimes. Okay? All right. I guess we'll just get into covalent, and then I'm sure I forgot to write something there, but we'll get it. Let's draw our first covalent compound, or I shouldn't say it's not a compound. We're going to start with the diatomics. The diatomics contain covalent bonds. Okay, so here's a hydrogen. Everybody put your pencils down. Just put them down. It's more important that you understand what's happening than you can draw, okay? Trust me, there'll be plenty of time to draw. So here's hydrogen. Okay, that's okay. I'm waiting for you. Okay, ready? Hydrogen has one valence electron. How many valence electrons does the hydrogen want?
0.
2. It wants to fill that valence shell. It could either go to 0 or 2. So let's go with the 2. Okay? It doesn't want 8. It only wants 2. That's why this is the simplest one, because we don't have to worry about anything that's going on out here. It wants another electron to come and fill in this spot. This hydrogen also wants to have 2. Through the magic of television, I can do this. Okay, so now I've got hydrogen and I've got hydrogen. If these two suckers get close enough to each other, they're like, hey, do you have an electron? This guy says, yes, I do, but I want to also. And then they go, Come on, we'll share. And then they go in there, they share, right? These two electrons are now called a bonding pair. Every covalent bond is made from two electrons, one from one atom, one from the other atom. Now, this right here is the covalent bond, but it is a specific type of covalent bond. It is called a single covalent bond. Oops, I don't have to write covalent twice. Okay? Those electrons that are right in between there are being shared by this hydrogen, which now has two, and this hydrogen, which now has two. The electrons that are right here are being used by this hydrogen and this hydrogen equally. They are being equally used because this has an electronegativity of 2.2 and this has an electronegativity of 2.2. And so therefore, neither one of them is going to win in a fight because they're exactly the same. So the electrons stay right in between them, equally distant from this nucleus and this nucleus are those two electrons. Now this thing is going to get messy if we draw it like that all the time. So what we can do is we can draw one little line. That little line is also a single covalent bond. It's just another way of drawing it. This is with the dots, this is without. Okay? Now you can draw what H2 is going to look like. We good? Okay. We're going to do all of the diatomics. Now on the next page, or the next little section, don't write until I'm done, we're going to do fluorine, chlorine, bromine, and iodine. Each one of these has 7 valence electrons. Therefore, they're all going to look the same. Okay? So I'm going to use X to represent the F, the Cl, the Br, or the I. And I'm going to put 7 valence electrons on these. 1, 2, 3, 4, 5, 6, 7. And then I'm going to do another one because there's 2 Fs here. 1, 2, 3, 4, 5, 6, 7. The reason why I drew them like this is because I want you to see how they're going to go together. All right, so again, here's my fluorine, here's another fluorine. Look, I want 8. I want 8 too. Whoops. Okay, let's get together. Look what happens. You see that? What's this right here? What kind of covalent bond? Single covalent bond. And it works for any of these, fluorine, chlorine, bromine, or iodine. That X can be an F, a Cl, a Br, or an I. So let's label this single covalent bond. Ooh, that pen is fat. So we can have F going to F. We can have Cl going to Cl. We can have I going to I. And we can have Br going to Br. They all have a single covalent bond. And that single covalent bond is right here, right here, right here, and right here. Okay? Each single covalent bond has 2 electrons in it. Now these guys, you can finish copying it. Lost my water molecule. Okay, we all good? These guys out here, I'm going to highlight them. I'll highlight them. Here, let's make it bigger. Here, here, and here, and here, here, and here. Those are called non-bonding pairs. They are paired up, but there is nothing bonded to them. There's nothing out here. Non-bonded pairs. Sometimes they're called lone pairs. That's a highlighter. Lone pairs. Non-bonding. This is the only. This is a non-bonding pair. This is a non-bonding pair. This is a non-bonding pair. So this thing has 6 non-bonding pairs on it. It's getting a little bit crowded there. With all these dots, that's why it gets crowded. Sometimes we don't even have to write the non-bonding pairs. You could just do F to F. If they say draw the Lewis dot diagram, please make sure you put the dots on there. It says Lewis dot diagram, draw the dots. All right. How are we feeling? Okay so far? Okay, let's go to oxygen. Oxygen. Oxygen has 6 valence electrons. Here's another oxygen comes along. He also has 6 valence electrons. I need 8. I need 8 too. Oh, I lost 2 electrons there. I need 8. So he comes over and he's like, oh, we can form a bond. If you look here, does that guy have 8?
No.
He has 7. And this guy has 7. So it's not done yet. So what's going to actually happen is these lone electrons that are down here. Where's my pen here? Just giving myself some room. This electron over here is going to come up and is going to go in the middle. Now both oxygens have use of it. And this oxygen is going to move his electron into the middle. And he's going to that's why I said don't draw until I'm done, because you're going to be moving electrons all over the place. Okay? This now is 4 electrons in the bond. It is not a single covalent bond anymore. Now it is called a double covalent bond. Double covalent bonds have 4 shared electrons. So you want me to draw this neater for you? You see it. See, oxygen, boom, 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 oxygen. That's what it's going to look like. Now you're going to notice that I moved the non-bonding pairs of electrons so that they're kind of look symmetrical on both sides. Do you see that?
Yeah.
Okay, this is why. This is not on the Regents, but I'm going to tell you why, because you're smart and you deserve to know. Okay? This atom, here's the nucleus of the atom in the middle of the oxygen. I'll do it in purple. Okay? Has 3 regions around it. The region where this non-bonding pair is, a region where this non-bonding pair is, and a region where these bonding pairs are. If you have a circle, how many degrees are in a circle? 360. Let me get rid of this because now it's all, okay? If I break this 360 degree circle into 3 equal parts, the angle between this non-bonding pair right here and this bonding pairs is going to be 120 degrees. This bond angle is also 120 degrees, and this bond angle is also 120 degrees. That's called molecular geometry. It's just saying that these electrons, which are all negative, want to be as far away from one another as possible because they're all negative. They're going to repel, and the way that they can get as far away from one another as possible is to have the biggest angle between them, and that is 120 degrees because I split it into 3 locations. 1, 2, 3. If you have 4 locations, let's say I have something with 4 locations. Here's 1 location, 2 locations, 3 locations, 4 locations. The angle here is, it looks like it's 90, right? That's what it looks like. It's really 106.5. And the reason it's 106.5 is because we're talking about a 3-dimensional substance or a 3-dimensional thing. Hold on, let me break out this. And it looks like, you know, like when you were a little kid and you were playing jacks. You know what jacks are? That little toy? Okay? You know what I'm talking about? I gotta find more sticks. Of course, the other one. Some sticks are bigger than others, but you'll get the idea. See how it's 1, 2, 3, 4. It's 3-dimensional substance structure. When there's 4, this bond angle is not 90. It's 106.5. Okay? You don't need to know the bond angle. You just have to understand that it's not flat on a piece of paper like this is. It's actually a 3-dimensional structure. Okay? All right. So that's oxygen. Now, oxygen has a double covalent bond. It's got 2 non-bonding pairs of electrons. And so when I'm going to draw it, I'm going to draw oxygen, oxygen, and then I'm going to put my non-bonding pairs of electrons out here. Good to go? Okay, let's do nitrogen now. The last one for the diatomics. Nitrogen, 1, 2, 3, 4, 5. Nitrogen, 1, 2, 3, 4, 5. What do you think is going to happen? There's going to be a triple covalent bond in between them because this is going to hook up, these guys are going to hook up, and these guys are going to hook up. So you're going to end up with something that looks like this. Who said what? You okay out there? Don't be afraid. How much time we have left? Okay. I can get a few more done. You do, at 2 o'clock. Mandated. Don't they have that in, like, Spain?
Yeah, I think, but you have, like, you get out school, like, super late, like, at 5 p.m. or something.
You take a siesta at 5 p.m.?
No, like, you get out of school at 5 p.m. and then, like, you have to nap time in school or something.
Oh, okay. So they just push it back. Yeah. Moving to Spain. All right, Jaden's moving to Spain. All right, I'm going to recap. Okay? Single covalent bonds. So we had hydrogen going to hydrogen. We had chlorine to chlorine. We had fluorine to fluorine. We had bromine to bromine. These are just the diatomics. and we had iodine to iodine. Okay, those are our single covalent bonds. There's 5 of them. Then we did oxygen. Oxygen had a double covalent bond. Let's keep it consistent, Kaufman. And it looked like this. And then we had nitrogen with a triple covalent bond, and it looked like this. Okay. If you draw them with the little lines, you'd have H going to H, you'd have Cl going to Cl, fluorine going to fluorine, bromine going to bromine, and iodine going to iodine. And oxygen would have a double covalent bond. Ooh, too many dots. And nitrogen would have a triple covalent bond. So that's just a recap. Any questions on them? Good. Moving on. Let's go to water. Actually, let's do HCl first. It's a little easier than water. Alright, so here's hydrogen. It's got his one little valence electron. He's wandering around. And we got chlorine. Chlorine I'll do in red. He's got 7. What kind of bond is it going to form here? Single covalent. And this hydrogen is going to come in and is going to sit right there. Easy peasy lemon squeezy? Okay. I can really draw this H with a line, Cl, and put the dots if you wanted to. Much easier. Alright, let's do ammonia. NH3. Now NH3, please write down what that is because it's going to show up a lot. That's ammonia, not pneumonia, ammonia. The smelly stuff that you use to clean. Okay? We're going to draw it. What atom is going to go in the middle of my structure?
Hydrogen. Nitrogen.
Nitrogen. It's usually going to be the one that's only one of. Okay? So let's say nitrogen's going to go in the middle. Let's put my 5 valence electrons on nitrogen. And then let's come in with some hydrogens. I'll draw them in orange. Okay? So here's a hydrogen. That hydrogen's going to come in and it's going to bond right there. Another hydrogen's going to come in. He's going to bond right there. And another hydrogen's going to come in and he's going to bond right there. So we've got 3 single covalent bonds. You see that? 3 individual single covalent bonds. Now in this covalent bond that's right here between this N and this H, are the electrons being shared equally or unequally? Unequally. And the reason is because N and H do not have the same electronegativity. They're not unequal enough that one can rip the electrons away from the other, but they are unequal in the sense that one of those atoms is going to get a bigger share of the electrons than the other. So I should have shown you with this one. I should have been like, oh, hello, class. Let's say we have this. Let's say we have this. Okay? So let's say this is the molecule that I'm looking at. These electrons are being pulled by the hydrogen and the chlorine. Where are they going to be closer to? Are they going to be closer to the hydrogen or closer to the chlorine? Okay. Well, let's look. Hydrogen's electronegativity is 2.2. Chlorine's electronegativity is 3. Help. 3.2? 3.4? Number 17. 3.2. Okay? So now these electrons, you would think after 30 years I'd know those. Alright, so these things are being fought over, right? This is not bigger than 1.7, so the electrons are not getting ripped off the metal and put on the nonmetal. They're still being shared, but they're being shared so that they're just a teeny tiny bit closer to chlorine than they are to hydrogen. See that? Okay. There's a special name for that type of bond, but we'll save that for tomorrow. Any questions on that? All right. Let's do water. Put a big star, a heart, a smiley face, a fire-breathing dragon. That's not red. His fire is red. He's got scales on him. That's a pretty good dragon. You should be very impressed. I'm impressed. Okay, why am I making such a big fuss about this? Because they ask you to draw water from now until June. You have to be able to draw water. Have to. So let's start with the formula for water, which is H2O. Which element's going to go in the middle? The oxygen. All right, so let's get the oxygen out there. Okay, oxygen has 6 valence electrons. I'm going to put them on. Okay, now there's 2 sites. There's a site right here and a site right here where bonds can form. Hydrogen's going to come in. Let's make hydrogens blue. Hydrogen's going to come in, and hydrogen's going to say, hey, I need another electron. And oxygen's over here saying, hey, come over here. Okay, so hydrogen's like, I'm coming, and there it goes. This is not anything. This right here is a covalent bond. Is it sharing the electrons equally or unequally? Unequally, because they're not the same element. So they're going to be unequal. And then another hydrogen's going to come along, and he's going to put his electron right there. Now, remember back a long, long time ago, probably in October, when I told you to please draw your Lewis dot diagrams like that, where I said start at 12 o'clock, and then 3 o'clock, and then 6 o'clock, and then 9 o'clock, and then 12 o'clock, and then 3 o'clock. Okay? If you chose not to believe me, and you do something like this, where it's all wacky and out of order, now when your hydrogens come in, they're going to sit here and here. Do you see the difference? Okay, now, this is not wrong, but you're 14, 15, 16 years old, and you don't know enough to understand the difference between this and this. So let me show you the difference between that and that. Here's a water molecule. Do you see it? Okay. Now, when you're looking at the water molecule, now I have to do this for Michelle. She's not here, so hold on a second. I got to put some light on the subject. This is what a water molecule looks like. This is red, yellow, yellow. One oxygen, 2 hydrogens. Okay? Just give me 1 second, then I'll give you your break. This right here is this. Okay? This right here is this. HOH. You are looking at it from a different angle. Or this. You see it? Okay, so this looks like this. This is the way I want you to draw it, because what it does is it shows the shape of this molecule to not be in a straight line. If you look at this, you think that all these atoms are lined up perfectly straight. They are not. They are bent like this in a water molecule. That's going to make a difference when we talk about molecular geometry and what the shapes of those molecules look like. Okay? All right, take your break. Let me finish this up on here so that Michelle could see. All right, so you got oxygen with 2 hydrogens. So it looks like this. No nap time. It looks like this. However, if you do this, you're looking at it like this. H-O-H in a straight line. That's this one up here, H-O-H. It's really not in a straight line. It is bent. It really looks like this. That's why I want you to draw your water molecules looking like this. All right, let me stop this tape and I will start a new one next period.